Welcome to chapter 3, part 2. I hope you guys are doing good. I'm going to keep gathering my things. As you guys kind of come on in and we get ready. So, today will be chapter 3, part 2. Otherwise known as how to use a balanced chemical equation, how to operate balanced chemical equations, how to calculate and solve for the limiting reactant. So hopefully things are going well. It looks like you guys are starting to get here. I'm obviously here. It's raining in Jacksonville today, so I guess that's kind of exciting. Let's see, other excitement. We will meet this week. Once, not quite yet, we'll give a few more people a chance to hop in to show up today before we talk about a little business. If you have questions, feel free to drop it in the comment box. I'll read those and answer those as we have a chance. Chapter 3 is like a third of the way through the semester, so we're moving along. It's coming along. Chapters 1, 2, and 3 are the beginning. And so we're almost done with those, and then we have 4, 5, 6 on exam 2, 7, 8, 9 on exam 3, and then just chapter 10. So we're just so close. Things are going well. I miss getting to see you guys. Sorry I didn't have office hours on Monday. Today is Wednesday, so we're going to review chapter 3, part 2, which you can see here. Let's see. I feel like there was something else I wanted to tell y'all before we got started. I don't know. The NFL starts this week, so that's kind of exciting. The Fighting Texas Aggies, we all know I love them. They don't play till the end of the month, so I'm excited about that. If you have any questions or want to say hi, go ahead and drop it in the box. I'm super excited that y'all are here. Other exciting news. Your weekly assignments for chapter 3 should be posted later today. They are graded. I just forgot to hit publish. Otherwise, it kind of looks like things are coming along. The chapter 3, part 2 assignment will get posted here in when I go back to my office after this. I need to bring a light in here. It's kind of dark. But trying not to carry around like a whole tray of stuff. Let's see. Other things. I've noticed some of you guys are not quite watching as many of the lecture videos that I've been posting. It only looks like we've gotten about 40 views for the chapter 3 parts 5 and 6. Maybe a little bit more than that, but definitely not as many as are enrolled in this class. So we do want to make sure we are looking at that kind of stuff. I am going to make this brighter. There we go. A little bit better. Actually, like so much better. Crazy. Let's see. Today we have 6 questions today, I think. I forget who made the suggestion, maybe only 5, last week, to just make the font smaller for my subscripts. It worked. I'm so excited. I mean, it's a little like, but it definitely worked, so we could definitely see what they're supposed to look like instead of just all big numbers. So I'm pretty excited about that. If you guys have questions, if you have thoughts, I know that SI is running this week. For sure in my Friday announcement, but my guess is that the exam 1 reviews will be next week since exam 1 is next week. All of the information for that, everything you could possibly want to know about exam 1 is coming on Friday. So in your weekly announcement, it'll have like the usual, like don't forget to turn in this and don't forget to turn in that. Then the entirety of the rest of it will all be about exam 1. So make sure you read it, make sure you look at it, make sure if there are tasks to do, you make sure you do it. There'll be a lot of good stuff in there. So it's all coming. Don't panic. Which does mean that there will not be a live next week because the exam will be during our class time. So, but again, it's in the announcement. Oh, I'm sorry if I'm giving you a fright. It's coming, but it is not going to be that bad. So, any other questions before we get started? If we have extra time, then we will go ahead and maybe do some other things if you guys have questions. If no one has questions, then we'll just kind of hang out. Nice. I like your hello exclamation point, Alexis. So hi to you too. Looks like Kajal is here and Zahara is here. So I'm excited that we're all here today. Okay. If no one has any questions, and if you do, we'll just take a break after question number 1. So, no one can read that with my face in there. Well, I don't think that's quite working the way I'd hoped. But we're going to try something. Sunny asked, will this live be recorded? They are all recorded. So all of these videos are on my channel. They are under, I think, fall 2020 chem lectures. So the live videos upload under a different tab. So if you can't come right now, that's okay. You can watch this later. I hope that helped. If you have a hard time getting it, send me an email and I'll send you a direct link. Okay, that didn't do what I wanted to do, so we won't do that again. Okay. So our first question says that ammonium phosphate, which gives us a compound formula, which is NH4, parentheses 3, phosphate, is an important ingredient in fertilizers. It can be made by reacting phosphoric acid with ammonia. So now in this question, there are a number of things where it maybe has the, like phosphoric acid isn't in there, and neither is ammonia. On the exam, it will mostly be written out, and if it's not, it's something that you should know how to name. So phosphoric acid for exam 1 would be included, but it's just not in this question. So it asks, what mass of ammonium phosphate is produced by the reaction of 15.392 grams of phosphoric acid? So what do we need to do first? So first, we need a balanced chemical equation. So a balanced chemical equation is always step 1, unless you have one, and then we can skip to step 2. So let's think about a balanced chemical equation. So we have ammonia, which is NH3, and we're going to add phosphoric acid, which is H3PO4, and that's going to give us, make sure I'm still in frame, NH4, 3PO4. So when we look at this, it's a little bit hard to think about how do we balance this. So one thing we can kind of look at is we have NH3, and we have phosphates, and we have these hydrogens right here. So it turns out that if we add a 3 right here, 3 nitrogens on both sides, good. 9, 10, 11, 12 hydrogens, 12 hydrogens over here, and PO4 and PO4. So we have a balanced chemical equation. Now, if I was asking about it, it would have included states for this, like NH3, gas, liquid, solid. Then you could include that. If I don't tell you, you don't need to make them up. Okay? So don't try to figure out what the states are. Just use what you got. So now it asks, what mass of ammonium phosphate is produced by the reaction of 15.392 grams of phosphoric acid? So what we're going to do is we're going to start with this, and we want to calculate how much of this. Now, one thing students often like to do is basically to say, well, we could just say 15 grams of one gives you 15 grams of the other. That doesn't really work. So what we're going to do first is write down the molecular weights. So don't forget, the molecular weight is just totally up the masses from the periodic table. If you want to review that, you can watch last week's collaborative problem-solving session, or at the end, we will look at that again. So ammonia is 17.04 grams per mole. This is 98.00 grams per mole. And this is 149.12 grams per mole. So we've got some questions. So Jeremy asks, do we need to know what phosphoric acid is? Not at this time. We will memorize acids in chapter 4, but today I would give you phosphoric acid on the exam. So Kajal asks, why is it NH3 on the reactant side if NH4 is on the products? Isn't it NH4? So it turns out that ammonia and ammonium sound the same and look very similar. So ammonia, A-M-M-O-N-I-A, and ammonium are totally related, and ammonia is NH3. This is what we will learn in our next chapter, a weak base. And ammonium is the ion of NH4+. So ammonia interacts with phosphoric acid to create ammonium phosphate. So it's not just a typo, but one and how they interact with each other we'll learn more about in the next chapter. But ammonia is a chemical component in ammonia and ammonium. One is NH3 and one is NH4+. So it's a good question. So this one is NH3 and this one is NH4. Good question. Is that all the questions I had so far? Yes. Okay. So the next thing that we want to do is to actually solve this problem. Now, when we think about the solving of a conversion of our starting material to an end product, we need to convert in a mole-to-mole ratio. So mole-to-mole ratio means that we need to figure out how many moles we started with and then convert to how many moles we have at the end. So what we're going to do is we're going to take our 15.392 grams of phosphoric acid and we want to convert that to moles. So we're going to use our molecular weight of 98.00 grams in 1 mole of H3PO4. So now we have the ability to have moles of H3PO4. So the thing we need to do next is to convert moles of H3PO4 into moles of product. So now we're going to use the stoichiometric ratio. Those are like the big numbers in front on an equation. So we're going to have for every 1 mole of H3PO4, it makes 1 mole of NH4,3PO4. So all we've done is taken our mass of H3PO4 and converted, using the molecular weight, into moles of H3PO4. We converted using the stoichiometric ratio, which in this case is 1 to 1, or 1 to 1. So now we have moles of we'll just say ammonium phosphate. But it asks about mass, and so mass is always in grams. So then in 1 mole of NH4,3, I'm a little lost, PO4, there are 149.12 grams. So when we plug this all into our calculator, what we're going to get is 23.421 grams of NH4,3PO4. So it's important to make sure that your sig figs is right. So in the question, if we look right over here, there are 5 sig figs. And if we look at our answer, we also have 5 significant figures. So it's 23.421 grams of ammonium phosphate. So what questions do we have about how to solve a question where we are not provided a balanced chemical equation, which is number 1, step 1, always step 1. Step 2 in this case is going to be to think about what is our molecular weights. Then we're going to convert using the molecular weight, the stoichiometric ratio, and the other molecular weight in order to get out grams of product. If you don't have any questions, you can write that in the comment box too. I always like to hear that. Give you guys a second just in case. Oh, but I'll step out of the way. Be close so you can tell that I haven't left you. But just to reiterate, the grams of H3PO4, the molar mass, the stoichiometric ratio, and then the molar mass of the other. One thing I hear a lot is that students are like, I don't know what to do first, second, third, last. So if you write out all of your units here, then you can go over, you can basically cancel them out as you go. So we have two good questions. Cassidy asked, is there a video that goes over naming them? Yes, it is the chapter 2 video. It's an older video. So if you're only looking at my channel on the recent uploads page, you're not going to find it. You can find it if you go to the chapter 3, no. Naming is in chapter 2. If you go to the chapter 2 playlist, it is whatever, I think it's the 4th video on the playlist. I'm going to try to figure out, it's on my list, to figure out how to make a little sign at the end that says click here to watch the next video, because that seems helpful. If you have thoughts on how I can make it easier for you guys to find videos, let me know. So Jordan asks, are we assuming that phosphoric acid is the limiting reactant? We are. So in a problem where it only gives you one mass, by definition, or maybe not definition, but we can assume that it is the limiting reactant. So in this question, because we were only provided with the starting material here, we're going to assume there is so much of this that it doesn't change how much product you get. So it's a great question. If you're trying to figure out is it a limiting reactant question or not, it will almost always say calculate the limiting reactant, or it will say in the problem, it would have given you 15 grams of phosphoric acid and some other number mass of ammonia. So, any other questions on number 1? Otherwise, we will look at number 2. Go ahead and make that go away. So you may not have noticed what just happened, but, sorry, these are mirrored. There's a typo in the equation. So it is, in fact, 6 and 2 on this side. If you've already done the worksheet, you should be like, I don't think this equation is balanced. I fixed it on my, not cheat sheet, but my solutions, but I must have forgotten to upload it on that one. So we have airbags in cars are filled through the decomposition, so a decomposition reaction, of sodium azide using the following balanced equation. So how many grams of sodium azide are required to form 13.56 grams of nitrogen gas? So we have a balanced chemical equation, which is great, but we'll rewrite it. 2Na(N3), which is sodium azide solid, decomposes into 2 sodiums, solid, plus 6 N2. Gas. This equation is not super balanced. It is balanced, but we do talk about how we actually want all of the stoichiometric ratios to be divisible by 2. So it should, in fact, be 1 sodium azide gives you 1 sodium. No, that was right. 3, 2, 2. Let me fix this. Sorry. My bad. Okay, now we're ready. However, my math is going to be wrong, so we're going to have to fix it. We're going to have to check it. So now we need our molecular weights. So the molecular weight is 65.02 grams per mole, 22.99 grams per mole, and this is 28.02 grams per mole. So now that we have our molar masses and a balanced chemical equation that I fixed and unfixed, so that's exciting. So from here, we're given the mass of nitrogen. So usually we think about how much product is created. But in this case, we know how much product we have. So we want to know how much reactant we need to start with. It's very similar to what we did in the last problem. We're just changing the elements that we're going to look at. So the first thing we're going to do is write down our 13.56 grams of nitrogen gas. So this is our ending material, but we want to calculate the product. Good. So from here, we're going to convert 28.02 grams and 1 mole of N2. Now we need to use our stoichiometric ratio. So in the last example, it was 1:1. This one is not 1:1. So the moles of N2 is going to be 3 to 2 moles of sodium azide. So there are 3 moles of N2 for every 2 moles of sodium azide. Now we want to convert that to grams. There is 1 mole of sodium azide is equal to 65.02 grams NaN3. So why don't you try to plug that into your calculator and see what you guys get while I do the same. So hopefully, as you've plugged it into your calculator, I'm using my phone because I totally forgot my calculator today. So it is 20.9772 grams, but that's 1, 2, 3, 4, 5, 6. 6 significant figures. But the problem only has 4. So we need to trim that back, and our final answer will be 20.98 grams of sodium azide. So as we think about this example, what questions do we have? So we don't have a limiting reactant. We could have also calculated how much sodium we would get produced in that case. So Camillo asks, how come it's called sodium azide and not something like sodium nitride? This is a really good question, and it's possible that it is also called sodium nitride. Sodium azide is a specific chemical that is outside of what you are supposed to know. So if sodium azide came up, I would provide that information to you. So sodium azide breaks a lot of the normal rules because in this case, the nitrogen isn't actually functioning as its normal -3 charge. It's doing some other weird things. So in this case, I would provide that to you. Why it is called sodium azide, I don't know. That's basically its chemical nickname. But I do promise on the exam, if it is not following the normal naming rules, then I will provide the name for you. Or it would have said, like, how many grams of sodium azide, open parentheses, NaN3, close parentheses, in that way. So you will not be asked to come up with things that violate naming rules or that, frankly, misbehave in terms of the way that we've already talked about them. Good question, though. Other questions about number 2 before we move on to number 3? We've got 25. I will double check my math. So Avery, I'm trying to figure out where you might have gone. Oh, you solved it. Glad to figure it out. It's never a problem to ask. I really like that you're plugging it in on your calculator. If I could give you like a shout out for doing that, I would, but I'm kind of new at all of these things. Glad you guys figured it out. All right, so let's look at number 3. So in number 3, it says the decomposition of KClO3 can produce small amounts of O2. Nifty. How many grams of O2 can be prepared from 4.5 grams of KClO3? And then we're provided a balanced chemical equation that my face is in the way of, to where we have 2 KClO3 solid decomposes into 2 KCl plus 3 O2. You can always double check those. I'm pretty sure I balanced those correctly today. But let's erase the board and then we will start again. So in this case, we're going to rewrite the balanced chemical equation, which you don't have to do. Actually, I'm going to try. No, I'm just going to rewrite it because I'm not that fancy. 2 KClO3 solid decomposes into 2 KCl solid plus 3 moles of O2 gas. So we have a balanced chemical equation, which was provided, so that's good. But we're going to need the molecular weights. Now, I have been providing you all of them on the exam, on the homework, on Alex, on anything else. You really can just do the ones that you need. I'm just giving you all of them so that you have them, okay? In case you want to do something else. So the molecular weights here are 122.55 grams per mole, 74.55 grams per mole, and then 32.00 grams per mole. So from here, we're going to convert, what did we get? We start with 4.5 grams of KClO3, and we want to convert that to oxygen. So we're going to take our 4.50 grams of KClO3, and it's the same basic methodology. To be honest, anytime we want to use a balanced chemical equation, whether it's limiting reactants or not, it's always the same steps. Convert to moles first. Okay, we can do that. 122.55 grams in 1 mole of KClO3. Now we're going to do the mole to mole ratio. Okay, good. So we're going to take our 2 moles of KClO3. Whoops, forgetting some units here. 2 moles of KClO3 gives us 3 moles of O2. Don't forget, oxygen gas is a diatomic, so it always comes as an O2. So big O, subscript 2. And in 1 mole of oxygen gas, there are 32.00 grams. So when we plug this all into our calculators, we should get 1.76 grams of O2. I'm trying to make my decimal points big enough. So, questions. So Map Lifted would like to know, and I won't repeat those because this is a teaching environment, what is this? So this is the ability to convert from a known quantity to another quantity using a balanced chemical equation. So this came directly from the 3.5 videos in that case. This is a class, this is a YouTube live class about Gen Chem 1. You're welcome to hang out. We are learning how to convert a starting material or a product to something else using the balanced chemical equation. Other questions you guys are having today? What are we thinking about these kind of things? Is this easy? Is it hard? Are you guys coping? Thoughts? If nothing else, we'll move to number 4. Doesn't look like you guys have any questions so far today. Hopefully things are kind of making sense. You guys. Well, this is a long question. Oh, I'm glad that you guys are doing good. I think it's kind of easy too, but it's just got to check in. Without seeing you guys, it's hard to know. So in this question, number 4, we are working on ways to improve the process by which iron ore, which is Fe2O3, is converted to iron using the following equation, which my face is in the way of. So Fe2O3, so iron ore, plus 3 moles of carbon monoxide, so just 1 oxygen, goes to 2 moles of Fe plus 3 moles of CO2. So if we start with 150 grams of FeO2, Fe2O3, what is your theoretical yield? So this is going to ask about percent yield, which is basically just a question about how much should you have made and how much did you make. Percent yield, in my opinion, is like the easiest calculation. So in the previous 3 questions, we all calculated the theoretical yield. The theoretical yield is how much do you expect to make. So in this case, we are going to convert, make sure this is correct. So we're going to take our 150.0 grams of Fe2O3, and the molar mass of that would be 159.7 grams, and 1 mole of Fe2O3, I think that's 0.70, multiplied. So in the balanced chemical equation, there's 1 mole of Fe2O3, which makes 2 moles of Fe, and then 1 mole, oh, this is so hard to see. 1 mole of Fe is 0.85 grams. Hold up. I'm going to try and move that. So now you can actually see a little bit better. We'll move the problem in a minute, because now it's still hard to read. So now, once we plug this into our calculator, we're going to have a theoretical yield. So our theoretical yield is 104.9 grams of Fe. That's hard to see, but we'll move it over here. 104.9 grams of Fe. So we get roughly 105 grams. So in the problem, down here somewhere, it says you only isolate 87.9 grams. So what does that mean exactly? Oftentimes in the chemistry lab, things don't go as planned. I've talked about how I like to bake. Y'all know that every time I make pancakes, I burn the first one. Or the last one, it's hard to tell. I give it to the dog, she's very happy. But that means that my yield, so if it was supposed to make 15 pancakes and I burnt one, I only got 14 edible pancakes, okay? So the percent yield is the actual divided by the theoretical, which in this case is 87.9 divided by 104.9. You got to multiply by 100, and that gives us 83.8% yield. Oops. Okay. We're going to make this. I'm going to just make that question go away because we don't need to look at it right now. And it's marking up my work. So the actual, you have to be provided that in the question, which I took away. So now we don't know what it was. But the actual is what you actually got. The theoretical is what should you have gotten if everything worked. Now, side note, I know most of you are not doing in-person labs this year. That's okay. Sometimes your actual yield, like if they had gotten like 120 grams, you can't really make matter, unfortunately. It probably means it didn't work very well. You didn't purify your product really well. So Cassidy asked, is 159.7 the molecular weight of Fe2O3? It is. So the molecular weight of Fe2O3 is 159.70 grams, and of Fe is 55.85 grams per mole. Other questions? Ooh, Carson asked that. Nice. I always like when you guys answer each other's questions. It makes me so happy. Okay, other questions about this one. And I will add a number 4, which you could get from the handout just in case you were like, I don't know where we are. Any other questions? Or we'll start talking about limiting reactants, which is many people's least favorite. Any other questions? Looks like we're moving along. I will erase the board in case you guys have some before we move on. So, our next question. This is a word question. It's really wordy, but that's okay. So, it reads, if 15.289 grams of aluminum hydroxide reacts with 17.293 grams of sulfuric acid to create aqueous aluminum sulfate and liquid water. We could stop right there and be like, whoa, but we're not. We're going to keep going. So then it says how many grams of aluminum sulfate would be created in this reaction? How many grams of the excess reagent remain? Good question. If they only collected 12.403 grams, what is the percent yield? So this is like a combo question. It has a bunch of different parts. You should expect to see stuff like this on the exam, where you would need to write and balance the equation. Then you would need to figure out the theoretical yield in the limiting reagent, how much excess reagent remains, and how much is what their percent yield is, okay? So first things first, balance chemical equation. So we're going to start with, make sure I'm in the right place, our aluminum hydroxide, AlOH3, which is a solid. So aluminum has a -3 chart, a +3. Hydroxide has a -1, so 3 to 1. Got it. plus sulfuric acid, which I would have given you, H2SO4 liquid. And that gives us aluminum sulfate, which is Al2SO4 aqueous, plus H2O liquid. Now we need to balance this equation. Can't really see. So when we start to think about this, balancing equations just tells us we need to balance things. So we want to start with something. So I'm going to start with this compound, and I want to make it match on the other side. So if we have 2 aluminum here, I'm going to put a 2 right here. So now the aluminums match, 2 on this side, 2 on that side, okay? Let's leave the hydroxides alone. We're going to come back to those. But the sulfates are next up in my list. So we know that there are 3 sulfates based on the aluminum sulfate compound. So let's just put a 3 here. So now we have the right number of sulfates on both sides. So what's left over is a water. So we have 6 OHs left over and 6 hydrogens, which form an HOH, or water. So we're going to put a 6 in front of this. So we now have a fully functional balanced chemical equation. I'm going to go ahead and write up the molecular weights so we can do all of our calculations with them. So the molecular weight of aluminum hydroxide is 78.01 grams per mole. Sulfuric acid is 98.09 grams per mole. Aluminum sulfate is 342.17 grams per mole, and water is 18.02 grams per mole. Now, here's where it's going to get a little bit tricky. So if you watched in the videos that I posted, some of the things that we can do is I will always calculate from both starting materials in order to figure out what is the excess and what is the limiting reagent. So we're going to start with that calculation. So the first thing I'm going to do is take my first reagent, which in this case is the 15.298 grams of aluminum hydroxide. And I want to convert that to figure out the mass of sulfuric acid. Now, you may have watched other videos, not produced by me, and they will show you other ways to do it. If you go to SI, they may show you a different way. I'm going to show you ways that get you to the questions I know I'm going to ask on the exam. I like the question right here. How many grams of the excess reagent remains? So if you do the product-to-product calculation, which I will not be showing, it will be hard to answer this question. Now, that's okay. You can do that. You'll just have to do some back calculations later. It's the same amount of math. It's just in a different order. So we're going to convert our 15.298 grams of aluminum hydroxide to sulfuric acid using the molecular weight of 78.01 grams and 1 mole of aluminum hydroxide. There are 2 moles of aluminum hydroxide for every 3 moles of H2SO4 and 1 mole of H2SO4. There are 98.09 grams, which gives us 28.85 grams, which you can just barely see. So this tells us to use up all of the aluminum hydroxide, we have to use all of this. Oh, come on. Did I really get those backwards? Shoot, I did. Hold on, let me go plug this back in my calculator. going to change the final answer just a touch. It's going to make it 28.81, which I think you guys can see, just barely. So when we think about this, it says to use up all 15.289, thank you for catching that, grams of aluminum hydroxide, you have to have 28.01 grams of sulfuric acid. So we only have 17, which is a good sign, which tells us that the sulfuric acid is going to be our limiting reactant. But it doesn't tell us how much of the aluminum hydroxide is going to be left over. So you could have equally chosen to start with the sulfuric acid, and then things might be a little bit easier. So from here, we're going to convert our 17.298 grams of H2SO4 multiplied by 98.08 grams in 1 mole of H2SO4. There are 3 moles of H2SO4 for every 2 moles of aluminum hydroxide. And in 1 mole of aluminum hydroxide, there are 78.01 grams, which says that we need 9.1686 grams. Now, in order to calculate how much of the excess reagent, we need to, 1, identify our limiting reactant. So, make sure I'm still on the board. H2SO4 equals limiting reactant. Good news. The excess reagent in this case is going to be our aluminum hydroxide. So we're going to take our 15.289 grams minus the what we use, which is 9.1686 grams, which I need to fix. Did I get all of these backwards? Nope, I just had a brain fart. It is supposed to be 983. I am so sorry. So because I screwed up the math on the other one, let's fix that. So 15.289 minus 9.1686 gives us, go ahead and finish that. Six point 111 grams excess aluminum hydroxide. Okay. We have some questions. Nicole got 28 point. Let me plug those in. So, yeah, sorry. So Emily asked if I'd gotten a number wrong. Yes, I need to write in bigger font when I solve these problems because I read a 3 as an 8. So I will double check my math for the first calculation, which is 15.289 divided by 78.01. Multiply by 3, divide by 2, multiply by 98.08. 09. So I think it's 0.84. Sorry, I need to bring a real calculator here. So Nicole is correct. I don't know what number I deleted the last time. Okay. So we've done a lot of work. We've asked, we've answered. What have we answered? Really only just question 2, which is how many grams of the excess reagent remains, which is good, but we need to figure out how much product we're going to get. So if 17.293 grams of H2SO4 is our limiting reactant, we need to use that to determine our product. Now, I'm going to step out of the way so that if you want to, I'm not advocating for screenshots, but I'm going to erase most of what we see here in order to solve the remaining questions about how much will be created and what is their percent yield. So if you have any questions, go ahead and drop them in the comment box. If you don't, before I do that, so Nicole asks, and you won't be able to see this because I'm standing in the way, for our final answer of the excess reagent, the 4 sig figs, yes. So the 4 sig figs here, make that a G, come from the fact that this number has 5, but 3 of them are after the decimal place. This has also 5, 4 of which are after the decimal place. In subtraction, it's about the number of decimal places. So in this case, the excess reagent, you can't get the 4th decimal place here, which I think is a 4, because this number doesn't have a place there. So in addition or subtraction, the number of sig figs are only determined by the answer at the end of by the number of digits after the decimal place, sorry. So in that case, the 15.289 minus 9.1686 can only have a total of 4 sig figs due to the decimal place digits. Did that answer your question? Or did I say a lot of things that didn't get us anywhere near an answer? Y'all, I don't know what's happening. I also get what Catherine gets, so that would change this to 6.120 grams. Which is exciting. Sorry about that. Okay. I'm going to go ahead and erase pretty much all this. I'm going to erase everything from here down. We'll leave this stuff over there so that we can calculate the amount of product we should get in this case. Oh, shoot. I bet you, okay. The 4 sig figs for H2SO4, which I just totally erased. Oh, yeah, there should have been 5, Nicole. So in 17.293 grams of H2SO4, we are going to convert that in as our limiting reactant to the product. I'm so sorry about that. There are 98.09 grams in 1 mole of H2SO4. There are 3 moles of H2SO4 for every 1 mole of Al2SO4(3), and then 1 mole of aluminum sulfate. There are are 342.17 grams. When we plug this into our calculator, we get, hopefully, 20.107 grams of aluminum sulfate. So now that we have our theoretical yield, which is basically determined by the limiting reactant, we can now go from here to calculating our percent yield. So they only collected 12.403. So we'll do it over here. Percent yield is 12.403 divided by 20.107 multiplied by 100, which gives us 61.685% yield. So this is a very long problem. It should take you a long time to do it by yourself. Just so that you're not feeling like, well, it shouldn't take very long. They do. So in this case, once we identified the limiting reactant, we took that and converted it to product. You could have also just taken both of your starting materials and converted those to product. That will get you the theoretical yield. The limiting reactant identifies the least amount of product created, so you can do that. That is one way for that to work. However, you'll have a hard time doing that. Aw, man. I had a late meeting. I was going to go through and double check all my math so we didn't have this again. But let's see. 293 divided by 90. I get 20.10. I think it should round up to 08. Yes. I know it feels like I don't like it when you guys catch my problems, but I like my mistakes. I do. I'm thrilled to death that you guys are working the problems along. I will endeavor to have less math mistakes next time. Okay, any other questions about number 5? Otherwise, we will solve our last problem and hopefully finish up right about on time. So I am going to go ahead and erase the board. If you have questions, I will figure out how to rewrite it so that we can solve this last question. Okay, so our last question of the day, number 6. Gaseous methane, which is CH4, reacts with gaseous oxygen to produce gaseous carbon dioxide and gaseous water. Great. What is the theoretical yield of carbon dioxide formed from the reaction of 4.65 grams of methane and 34.0 grams of oxygen? So this question has a lot less parts than the last one. It will only have mildly less work, though, unfortunately. So we're going to start with our balanced chemical equation, which is CH4 gas plus O2 gas gives us CO2 gas plus H2O. Hold up. I'm going to just rewrite that a little bit lower so we can all see it. CH4 gas plus O2 gas goes to CO2 gas plus H2O gas. So now we have an equation, but it's not yet balanced. So we're going to start by checking carbons. 1, 1. That's nice. So there are 4 hydrogens here There are only 2 here. In order to balance that, we need to put a 2 in front of this. So now our hydrogens are balanced, but our oxygens, we have 2 on the left and 4 on the right. So we're going to put a 2 here. Then we need the molecular weights. So there are 16.05 grams per mole. There are 32.00 grams per mole, 44.01, and 18.02 grams per mole. So from here, we need to identify the limiting reactant. So in this case, we want to just start with one of these 2. I tend to start with the first one in the problem. You don't have to. You can pick either one. So we're going to start with our 4.65 grams of methane and figure out how much oxygen we need. So we're going to take our 4.65 grams of CH4 and convert it to oxygen. So we're going to use the molar mass, which is 16.05 grams in 1 mole of CH4. There's 1 mole of CH4 for every 2 moles of O2. In 1 mole of O2, there are 32.00 grams. So that gives us 18.5 grams of oxygen are required. So I do this calculation because I'm always on the exam, I'm probably going to ask about the excess reagent. Now, in this moment right here after this calculation, 4.65 grams of methane requires 18.5 grams of oxygen. From here, we don't need to do much more math to identify our limiting reactant. We don't. Because either way, whether you started with oxygen or with methane, this tells us that methane is our limiting reactant. If you had started with oxygen, it would tell you that it requires more methane than you have, therefore oxygen cannot be the limiting reactant. It has to be the excess. So I'm going to go ahead and now just calculate, using my limiting reactant, how much it asks is about carbon dioxide. So we're going to take our 4.65 grams of CH4 to 16.05 grams in 1 mole of methane. There's 1 mole of CH4 for every 1 mole of CO2. In 1 mole of CO2, there are 44.01 grams, which gives us 12.751 grams. We're going to need to trim that back to match our significant figures, which gives us a final answer of 12.8 grams of CO2. So, Nicole made a comment. And I cannot respond via text because then I will stand in front of the problem. But I want you guys to ask questions. I wish that we could do it more personally. I know that writing in a text box is kind of hard, but I like that you're asking questions. It tells me that you're trying, and trying really is the best aspect. So when we think about this answer of 12.0 or 12.8, we know that it has the right number of sig figs because it's 4.65 grams of methane, which is what we started with. So this is a question, I don't remember if this is similar to an Alex question. So I'm trying to pull things from Alex so that when you guys do your objectives, you can always come back to this and be like, now what did we do? So if Alex shows you a different method, or Megan does, an SI, or if you go to tutoring, or if you learned some other super cool way in high school, you can use all of those methods. They will all get you to the same right answer. This is just my preferred method, and so you don't have to like this method. You can pick something else. As long as I can follow your work and you didn't just like write down this answer, it's okay. I will grade any and all of that. So Kajal asks, can you explain again why methane is a limiting reactant? Sure can. So the calculation that I did converts the 4.65 grams of methane to how much oxygen is required. So in the videos, I talked about making peanut butter and jelly grilled cheese sandwiches. So this says to use up all of the methane, you have to have 18.5 grams. In the problem, we have 34 grams. So it isn't necessarily that the problem that, no. So 18.5 grams is less than what we have, which tells us that this is going to be our excess reagent. So what I will do, sorry, I'm trying to figure out which side of the board I have space on. This side. How far we're gonna go. Here we go. So if we were to convert the 34 grams, yeah, 34.0 grams of O2, this is gonna be kind of a weird calculation, but 32.00 grams in 1 mole of O2. And then there's 2 moles of O2 for every 1 mole of CH4. And then 1 mole of CH4, there are 16.05 grams. So you would need 8.52 grams of CH4. And so we know that in this case, the CH4 has to be the limiting reagent because to use up all of the oxygen, we need to have 8.5 grams. And that's not what we have. So Cassidy asked, are you going to release a practice exam? No, there's not a practice exam. There will be a practice ability to test all of the systems to make sure that you can access the exam. You know what you'll have to do. I've provided there are a lot of other resources that you guys will have access to instead of a practice exam. Jordan's right. There's worksheets, textbook problems. You can redo these assignments at a later date and recheck them. Other questions you guys have today? Do you have other questions about other material? So limiting reactants and percent yield is the last step on exam 1. So everything that we've covered up till now is what we have. On Monday, which we never meet on Monday. So on Monday at 3 o'clock, we are going to meet, we're not going to meet. I will be here on YouTube Live. I will create a series of, probably not all that many, but a handful of other questions, like review type questions. So for you guys to get one more chance to go ahead and look at, to ask questions. So if you realize over the weekend as you start studying, like, Dr. Malcolm, I don't know how to do any Alex question, any topic, you can send me that information in an email. You can write it on the discussion board that I don't think anyone's ever looked at on Canvas. And I will work an example for that. If you get stuck on an Alex objective this weekend, feel free to send me an email, and I will add that to my list of things to talk about next week. Otherwise, I don't have much else. We will have a review conversation on Monday. I know there is an SI review. I just don't know when it is. So I will get that information from Megan and include it in my announcement this week on Friday. I promise not all of your questions, but many of your questions will be answered on Friday. If you would like extra help with any topic, my office hours are on Zoom. You can access them from the homepage on Canvas. The next ones are Friday morning from 10 to 12. That's all I have today. If you guys have any other questions, I'll hang around. Nicole has one. Will the questions on Monday? Yes, everything will be available afterwards. So if you can't come on Monday, because we don't ever have class, both the live and the worksheet, because it'll probably be just like this, that will both be in the place where you could access those. So great question. There are very few one-time only resources in my class. I hope so, Nicole. My goal is to post that on Saturday and maybe add some later, but I will try to get those. I hope to get it out Saturday before midnight, but it'll be in the same place where these worksheets go so that you know where to look for it. But as soon as it's available, I will post it on there. We may not get to all of the questions because I may make more than we have. So again, if you have questions, feel free to drop me an email. Comments only mostly work, mostly because this stream is going to end here in a second. All right, any other questions? Otherwise, I will see you guys all on Monday or in office hours. Hope you guys are having a great week. Bye, guys.